Hello everyone, in this video we are going to learn about Bernoulli equations. Bernoulli equations are also sometimes referred to as reducible to linear differential equations. So let's begin by looking at the general form of such differential equations. Such differential equations look like dy by dx plus py equal to qy to power n, where p and q are functions of x only. So when we look at the form of this differential equation and compare it with the linear differential equations that we discussed in the previous video, we can see that they are very similar to the linear category dy by dx plus py equal to q, but this extra power of y which is attached to the right hand side function is distorting the linear format. Now let's look at this differential equation under certain special situations. If we take n to be 0 in this differential equation, then this differential equation is going to take the form dy by dx plus py equal to q, y to power 0 happens to be 1. So this differential equation takes the form of a linear differential equation only, which we know how to solve using the technique that we had learned in the previous video. So n equal to 0 gives us linear differential equation directly. Let's look at the situation when n is 1. When n is 1, this differential equation boils down to the following. It takes the form dy by dx plus py equal to q y to the power 1. So here also you have a y. So if we combine these two terms, then we see that dy by dx takes the form q minus p times y. Since p and q are functions of x only, so q minus p is also a function of x only, and then we have a y term on the right hand side. So it's basically splitting as a function of x times a function of y. So it's a separable differential equation which we know how to solve already. So that means the Bernoulli differential equations, that means this power of y is going to give us effectively something new only under the case when n is different from 0 and n is different from 1. If n happens to be 0, it's a known category, the linear category. If n happens to be 1, it's a known category, the separable category. If n is different from 0 and 1, then this differential equation dy by dx plus py equal to qy to power n is something that is of interest, and we should learn a technique of solving such differential equations, which is the intention of this video as well. Now I would like to make a comment here that n is generally a notation used for natural numbers, but don't get misled by this notation here. N can be any real number here. It can be any real power attached to the right hand side function. It may be fractional, it may be an irrational power. Any kind of real number is going to work here in the technique that we are going to learn here. So the procedure for solving such differential equations is the introduction of a new dependent variable. We are going to introduce a new variable, let's say z, which is going to be y to the power 1 minus the treble power. The treble power on the right hand side in the format is n. So if n is the power appearing in the differential equation, then substituting a new variable z as y to power 1 minus that power is always going to make it linear in the new variable z and x. So once it becomes linear in z and x, we know how to solve it using the linear technique of integrating factors and all those things, and then we are going to substitute the value of z back in terms of y to land into the final solutions. Let's learn this technique through an illustration. Look at this differential equation dy by dx plus 6 by xy equal to 3y to power 4 by 3. So if we have this differential equation with us and we compare it with the standard form, it's dy by dx plus p. So p is this, py equal to q y to the power n. So n happens to be 4 by 3. So it's a Bernoulli differential equation with n equal to 4 by 3, and according to the technique that I've just now told you, you have to introduce a new variable, let's say v or z, whatever you want to name it. Let's call it v or z, whatever is convenient for you. Just call it that. Let's take v to be the old dependent variable to the power 1 minus the treble power. The treble is 4 by 3 here. That's the extra power of y attached to the right hand side function. So taking the new variable as y to the power 1 minus that power is going to help us reduce it to linear in v and x. So let's simplify it further. So basically v should be taken as y to power minus 1 by 3, and this differential equation is automatically going to adjust everything and it's going to fit in the linear class in terms of v and x. So let's relate the derivatives, because v is something that we have introduced. Dy by dx was the old derivative. So let's relate the two derivatives by differentiating both the sides. When I differentiate this with respect to x, I get dv by dx, and the derivative of y to power minus 1 by 3 is going to be minus 1 by 3 y to power minus 4 by 3 into dy by dx. So that means I can write dy by dx as, taking things to the other side, it's minus 3 y to power 4 by 3 dv by dx. So that's the value of the new derivative. That's the value of the old derivative in terms of the new derivative. So when I substitute in the given differential equation, the given differential equation is dy by dx plus 6 by xy equal to 3y to power 4 by 3. Let's substitute this value of dy by dx here and simplify it a little bit. It takes the form dy by dx gets replaced by minus 3y to power 4 by 3 dv by dx. Rest I am copying as it is for now. So this is what the differential equation becomes. Now let's get rid of the coefficient of dv by dx. Let's divide by minus 3y to power 4 by 3 to look at the form which it takes after this substitution. This is the form which the differential equation has taken. Now one more step of calculations. So 6 and 3, they cancel out. So you have a minus 2 by x here, and this is y here, y to power 4 by 3 here. So that takes the form y to power minus 1 by 3. After combining the powers, y is y to power 1 minus 4 by 3, that's y to power minus 1 by 3. Everything is cancelling here, you are just left with the minus 1. But what was y to power minus 1 by 3? Look at your substitution. You had substituted v as y to power minus 1 by 3. So in the new variable system, the differential equation becomes dv by dx is added to minus 2 upon x. Y to power minus 1 by 3 is nothing but v. So the differential equation has converted into a linear differential equation in v and x. And that is what we had expected, because the substitution z or v equal to y to power 1 minus the trouble power is always going to auto adjust the derivative and reduce the given differential equation, which is Bernoulli to begin with, into a linear differential equation in the new system of variables. And now since it's linear in v and x, we can very easily solve it. We find out the integrating factor. This technique we had learned in the previous video, how to solve linear differential equations. You take out this p, raise it to the power e to the power, that integral of p dx is what your integrating factor is. So when we simplify it a little bit, it takes the form x to power minus 2. So the solution is given by the dependent variable, which happens to be v now, into the integrating factor is equal to the integral of the right hand side into the integrating factor. So let's integrate it quickly. To write it as v by x square is, the integral of x to power minus 2 is minus 1 by x. There's one more minus waiting here, so it becomes 1 by x plus c. So that means v is taking x square to this side is x plus cx square. But do not leave the answer in the v notation, because v was something introduced by you. V was y to power minus 1 by 3. So please do not forget to replace back the value of the old variable. The new variable was introduced by you. Do not leave the answer in v and x. The final answer is this. This happens to be the general solution of the given equation. So whenever you come across a differential equation which is looking very similar to the linear category, except this distortion which is in the form of an additional power of y on the right hand side, you can always make it linear through the substitution, which is going to be a new dependent variable equal to the old dependent variable to the power 1 minus the trouble power on the right hand side. This is always going to make it linear in the new system, and you can solve it the linear way. and then do not forget to replace back the old variable in the final solution. You should have a y and x system only. If the differential equation is involving y and x, your answer should also involve y and x. And that's the end of this video, where we have learned about Bernoulli equations. In the next video, I'm going to discuss another class of first order first degree differential equations, which are called exact differential equations. For now, that's all. Thank you so much for watching.